Okay, so I will try to. I don't know if I have the sound. Yes? Okay. I will not let you more time. I will present the solutions and how the code is supposed to work and what is the bug that you have in the last question, which is the most interesting. Of course, you will not have the time to reach the last question in half an hour, but at least you will see where are the difficulties. So just to give an overview of the code that you are supposed to implement, the basic idea is that we have the persistent memory here and the hard drive here, and we have two files. The first file is the nvmm.data, and the second one is the file out.dat. And what we want to do is, when we want to write something, we write it in persistent memory here in this buffer. And we have another thread that is named the cleanup thread that takes the data from the persistent memory and execute the write in the hard drive. So the basic idea is that since you write first your data in persistent memory, it's fast, but the size of a persistent memory is small. So if we want to have large files, we just have to copy the data from persistent memory to disk to have a very large space. Okay, so it gives you the overview. Now, in order to implement that, we need two variables. One, so basically the persistent memory itself is just a producer-consumer. The main thread produces data in persistent memory, and the cleanup thread consumes data. So it's not very complex at the end. So to implement a producer-consumer in shared memory, in persistent memory, we just need two variables to know where we produce and where we consume. Okay, so tail is used to know where we consume for the cleanup thread. So the cleanup thread will inspect what is at tail, and the producer produce at head. In the code, what we do is just that we keep an empty entry to identify when the log is full. Because if we don't keep here an empty entry, and we have head is equal to tail, we cannot know if the log is full or totally empty. So we use that to just here, we know that the log is full, because head is just before tail, so we cannot produce anymore. Here, if you produce something, you will not distinguish between a full log and an empty log. So how it works, the cleanup thread use tail and will advance tail and apply the operations. So here, the cleanup thread take E1, E0 and E1 and propagate everything to the disk and advance tail. So it's supposed to work as is. Okay? Everybody is okay with the principle? Perfect. So after, the main thread, the producer, can produce new value in the log. So here we produce a new write E6 that we add here. And during this time, the cleanup thread will apply the writes one after the other to the disk. So it's a circular buffer. Okay. The algorithm that we have works, but we have an issue when the log is full. And it's related to the fact that what we see in the caches is not what is in persistent memory. So here, in volatile memory, I mean the data that you see in your cache, in the volatile state of your applications that you have here, and here the persistent state. So what is actually propagated to the persistent memory. So let's take this state initially. We have the log is full. We have the tail in persistent memory, which is on E0. We have a copy of the tail in our volatile cache in the processor, which is also on E0. And we have the head just behind. Now, if we implement naively the algorithm, what we will have, we will have the cleanup thread that will propagate E0 on E1, just like that, just like I made. At this time, in volatile memory, so for the other threads, tail is on E2, but the state in persistent memory is still the old state, the stale state. We have tail that is still here, just because the cache line that contains tail is not propagated to the persistent memory. Okay? So at this step, the producer sees that we have empty cells and that we can produce in persistent memory. So the producer can create two new entries here, E6 and E7, advance here. And at this step, we don't have any guarantee that the tail is actually on E2. So if we have a crash exactly at this step, we have an inconsistent view of the world, because when we will recover after the crash, we will see tail on E7, and we will try to apply E7 before E2, E3, E4. So it means that we invert the order of the writes, which is quite a problem. Let's imagine you write x equal 1 here and x equal 2 here. You suppose that at the end you want x equal 2, but if you apply x equal 2 before x equal 1, you will have a wrong state. So this problem illustrates the problem of what we see in volatile memory and what is actually persisted. So to solve the problem, we don't have solutions with only a single variable. Because whatever the solution, if I use tail to synchronize my threads, and I use tail to know what is the last written value, I cannot use tail for the two purposes. Because at some point, I will have to advance tail when I consume something, and as soon as I advance tail, the other threads think that that tail is updated. So to solve the problem, what we need is two variables. One to synchronize the threads, and the other one for durability. And we have to split the implementation in two parts. So it's exactly what we can do with two variables. So here we have a volatile tail that is used to synchronize the producer and the consumer for the threads in volatile memory. And we have the p-tail, which is the persistent tail, that indicate what is actually propagated from the log to the disk. So now how it works. It's easy. We want to consume, so we have the cleanup threads that want to propagate E0 on E1. What the cleanup thread will do is the cleanup thread will advance p-tail here, but during this time, the volatile tail is still on the old, on E0. So for the producer sees that head and you don't have any room to produce for the moment, so you have to wait. And we propagate the data. And here we can use the psync primitive to ensure that ptail is propagated to persistent memory. So here with a simple psync, you will be sure that everything, that ptail has the correct value. And only after that, you can advance the volatile tail to ensure that you will not produce while ptail is late in persistent memory. So now we advance vtail, and at this step, we have the guarantee that we can produce because the ptail in persistent memory has a correct value propagated. Okay? You see the issue? Cool. So I will present the code just to I don't know if we can read the code. Okay, so in the code here, okay, so you can find the code that presents that. What is important? So you have the two files. So the NVMM the NVMM file is just your buffer in persistent memory. Here you have the file where you will apply the writes. Just to load the non-volatile main memory data structure, you use get NVMM, which is straightforward here. You just have to open the file to create it if it does not yet exist. Then you have to give it a size. So the size is the size of NVMM. And to map it in your virtual address space. Not very complex. Just I use these strange flags to adapt the code when we have a persistent memory or when we have volatile memory for our computers. Okay. Then what we do is after a crash, we have to recover. So it means that we may have pending writes in the buffer, in NVMM, and we have to apply them to the file out. So I will present the code of recover after, because it's easier to first see how we add the elements to NVMM, how we apply the writes, and then how we recover. The order is not very intuitive. So then we have to create a thread for the cleanup thread that will run in parallel with the application. And after, it's easy. We just perform a large number of writes by calling mypwrite instead of pwrite, which is the normal function. Okay? So, yes, and at the end, I just use the store to tell to the cleanup thread that it has to stop. Okay. So to add a write to the persistent memory, we just have to, so we can have multiple producers because we have multi-threaded application. So here the synchronization is between threads that execute mypwrite. And for these threads, they just have to find a new entry in the log. And for that, they have to advance head. So how it works, just we load head, then we compare head to the volatile tail, so exactly what we have here. If your head plus 1 is equal to the tail, it means that we don't have enough space in the log, so we cannot add a new entry. So in this case, it's the first test that you have here. So we load head, we increment it, and we compare the new index with the volatile tail. And if they are equal, it means that we don't have space and we have to restart. And we actively try to increment to find a room. OK. So now we are sure that we can produce a data. So we try to write the next index in the variable head. But we may fail because we can have two threads that are taking the same index here. They see the same index at the same time. And just the first one will be able to write the new value, and the second one will have to restart to find a new room, just in case of parallel execution of the two threads. I don't know if I'm clear. It's just a problem of multi-threaded applications that try to increment a number. So, in the same buffer, exactly, in the same variable. Okay, so now we are able to advance the head, and we have our index where we have to produce our data. Okay, here at the end of the line, you can see a small AESM pause. It's just an instruction provided by Intel that slows down the processor. Because one of the problems that we have when we have this kind of loops is that the processor will see that we always fail. We are looping, and the processor, the branch predictor of the processor will see, okay, each time I read next index, I have to restart. And the branch predictor will predict that we are looping, and the speculative execution inside the Pentium will start to execute multiple steps of the loop in advance. And when the value of VTail change, the processor will have to abort all the speculative read that were made in advance. And this slows down a lot the reactivity of the processor when VTail is modified by another thread. So we just slow down the processor with ASM pause to be sure that we don't execute in advance the speculative read when we spin loop here. Okay. So now we just create an operation. So to create an operation, it's not very complex. So here we have a pointer to the operation. We copy the data that we want to write in the operation. So the buff is just the data that you want to propagate to the disk here. Then we have two cache lines in an operation. One cache line where you will have the data that you want to write, and the other cache line where you will have the metadata associated to the operation. So here we add the second cache line we unqueue the cache line write back for the second cache line. Then we specify, okay, we want to access to the file fd at the offset off, and we want to write n bytes. So we write that. Then we add the cache line to the FIFO queue of cache lines that we have to propagate. And then we have a fence. This fence is very important because it ensures that the cache line here will be propagated before this write that commit the operation. Yes? Okay. The order of the two PWB is not important before. We can propagate this cache line or this one. It's not very important because in the worst case, in case of crash before the pfence, the entry is not committed, so it means that the operation does not exist. What is important is that we want to have the two cache lines, this one and this one, written to persistent memory in case of crash if committed is equal to true. Okay, so after here we have our fence, and then we can commit the operation. So here we know that if committed is equal to true, then fd and offset and buff are correct because they precede the pfence. Okay, and then we propagate committed. So why we have this PWB and this pfence is just for the next thread. We are sure here that when we will call again mypwrite, that the previous operation is committed when the new operation is started. Here it's just if you have just for the loop. Okay. Okay, so it's just a producer in shared memory that you have in volatile memory. Not very complex, not more complex than, except the problem of propagating the cache line in the correct order. Okay, so after we have the cleanup thread, and here the code is a little bit more complex. The cleanup thread will try to batch the writes. So it means that the cleanup thread will inspect the buffer, try to apply at most max jobs in a batch, and then advance the tail or the tail, sorry. It's just to avoid calling fsync for each operation, which is very costly, because fsync ensures that the data in the Linux cache is propagated to the hard drive. And we have to ensure that to be sure that data is propagated from the Linux page cache, because otherwise we cannot forget the operation. I will illustrate quickly. Okay, so the cleanup thread just inspects the buffer by starting from the tail. So here, sorry, I have the volatile. Okay, so tail is the persistent tail. Sorry for that. Okay, so the cleanup thread is running is using ptail to know if I have an operation to propagate. And for the cleanup thread, I just take the operation that is at ptail, and I just have to read the committed flag to know if I have an operation to apply. It's exactly what we do. So we take we have our current operation. I load committed. If committed is true, it means that the operation is validated by the producer. So here I simulate a crash. So if I pick a number, I crash everything, just to illustrate how the recovery works if you want to test it. It's not very important. What is important here is that I will, if I have something to apply, I have a write, a pending write, I call the Linux function to actually write the data from the persistent buffer to the hard drive. But here, pwrite just add the data that has to be written in the cache of Linux. The data is not yet propagated to the disk. Okay? So at this time, I cannot suppose that the data is reached the hard drive. So I cannot yet move my tail. Where is my tail? Here. I cannot yet move it. So just after, here I call fsync to ensure that the data that is in the Linux patch cache is propagated to the disk. So when this function returns, it's just like a psync for a hard drive. It's exactly the same semantic. We are sure that after the call to fsync, the data is persisted to disk. So since the data is in the disk, I can forget the operation in persistent memory. It is applied to the disk. So it's exactly what we do here. After the call to fsync, I can write that the operation is not committed for the next producer. And I can then propagate my cache line and execute a pfence before advancing the tail in persistent memory. So why I have to do that in this order? It's because if I advance tail and committed is still equal to true, in case of crash, when the system recovers, it may find a non-committed operation randomly. No, I'm not clear. Oh. Okay. Okay. So after, sorry, I'm a little bit lost. Now we manage, so here we just propagate, for the first part, we just propagate the operations from the buffer to the disk. Now we also have to manage the synchronization with the producer. It's exactly what we do in the second part of the code, where we advance tail here in persistent memory. We ensure that the persistent tail is committed to persistent memory, and only after we increment the volatile tail that unblock the producers at this step. So of course, if we don't have, we have to stop, we stop at the end. Okay. Okay. So now to recover, it's easy. We just have to inspect the buffer of operations and to apply each operation that is located in the buffer. So we start by at tail. If we see that at tail the operation is committed, which is this test, it means that we have a pending operation. We can apply it by calling pivwrite. So we do that for all the entries. And at the end, we just have to restart from an empty log. It's exactly what we do here. We just erase all the entries in the log by starting from the first one, and that's all. Okay. I don't know if you have questions. It was clear. Now, what you can see is that very quickly, we have just a producer-consumer. It's not something that is really complex, producer-consumer. And at the end, what you can see is that the code is a kind of spaghetti. It's very complex at the end. So it means that when we want to write correct code for a persistent memory, it's really tricky because we have to understand how the CPU synchronize with the caches, then how the cache line propagates to persistent memory, how the system execute writes to the disk itself. We have different steps, and it's quickly a mess. I don't know if you are convinced that it's complex at the end. So just to make this code correct, it took us almost 1 month to be sure that this code is correct when we designed the booster. Just for a few lines of code. At the end, we have two index and the advanced, not so complex intuitively. And the bug that you have here when you don't the reason why we have to use a volatile tail and a persistent tail and identify this bug took us days just to have the idea of the bug. So I don't know if theoretical researchers could help us to design tools able to automatically prove the correctness of algorithm. It could be very useful for me, I have to say. So that's all. No question? Yeah.
So, as I understand, this thing should boost the default tail layer. So, are there any numbers?
Yes. I can show you some numbers. So here you have the evaluation that we performed with the full system. So here we are, in the code that I presented, we only have the write. We don't have the read. So because the read is more complex, we have to first inspect the log to see if we have pending writes, and then we have to read. So here we evaluated our system with I don't remember which database. It's right. Okay, RocksDB and SQLite. And here you have the performance of SSD in pink, which is at 300 microseconds, which is approximately here in the figure. And the performance that we can reach with the booster, we are at the scale of 14 microseconds. So we divide by 4, 5 the latency, approximately.
How many paths do you write concurrently?
In this evaluation, if I remember correctly, we only have one single thread. And
How many paths?
files, I don't remember. I know that probably just one.
So yeah, in case of one file, I guess this optimization would work because, as you mentioned, the throughput of NVMe is almost the same as the throughput of the regular SSD drive. But if you have to write multiple files, I guess the count that couldn't stagger the whole system and it couldn't
It's exactly what we have here in this figure, where we have the throughput during time, and what we observe is that at some point the speed of the hard drive is too low for the producer. So the log is always saturated. Hmm? I don't hear you.
you are talking about the speed of not NVMe thread, but the regular thread.
Yeah. And at the end, when we have many a write-intensive workload, we saturate the queue, and the cleanup thread is blocked by the speed of the SSD. So at the end, we don't win anything. If for a very intensive write workload.
So yeah, maybe if you write a single file, this won't be a problem because, as you mentioned, the throughput is the same. So
Yeah.
you have the same throughput of writing into the queue, and as the cleanup thread, you free this queue with about the same speed. I guess.
Yes, except that the latency is not the same. The throughput is good, but the problem is that when you propagate the operations, you have to call fsync to ensure that the data is propagated, and here the latency matters. It's not only a problem of throughput.
Yeah. I understand what's the point of the solution is. I'm just saying that if you get to write to multiple files, all I'm saying it's interesting if you could benchmark these multiple times.
Yeah. We could. I confirm.
In probably in this case, the performance would be like it could be reversed.
Mhm. No, I really don't know how, with many files, how the system would behave.
The question about scalability. So you could create independent trees, independent buffer for each file, and you will get the same picture.
Yeah.
In fact, as I understand, it's not solves the hardware issues. It solves the software issues of throughput and latency inside of Linux right now, what we see. That you compile everything from Linux and C++, get a new way how to push the data to hardware, to hard disk, without any limitations that we have right now inside of the kernel of Linux. It goes through direct to persistent storage memory. That's all what we have. So you're going to avoid a lot of processing time inside of CPU and volatile memory.
Exactly.
So your trees go directly to write file. Right now you have no choice. You just use kernel Linux API and you are just waiting. You can't do anything. That's just a software solution how to write directly to disks without loss of data and do not use the default kernel of Linux. That's what you see.
Exactly.
Imagine
It's a kind of
like
kernel
additional
bypass.
driver.
Yeah.
Yeah. Also, I wanted to mention that I'm not sure if file descriptors are like good persistent identifier of a file. I mean, if the cache would happen, I'm sure that the file descriptors of the cache would be like referred to the same files.
Yeah, sure. In the exercise, we directly store the file descriptor, but it does not make sense after a crash. So in the actual code, we have a table at the beginning of the persistent memory where we have the name and the file descriptors that we were using before the crash, to retrieve the path of the files, of course. No, for the exercise, it does not make sense. I totally agree. No question? Time to go to it?
So, do I understand correctly that non-volatile main memory has, because of the direct access, has like no notion of the page fault, and do I understand correctly that this means that the latency memory access is more stable? And
Not totally. I didn't check, but I think that when you mmap a persistent file, Linux still use the on-demand paging mechanism. It means that when you return from mmap, you just have the reservation in your virtual address space, but probably that the Linux will fill the page table when you will access to the pages for the first time. So you will have a page fault, and then you have to find where is the page of the file and to map it. So I don't know if it's so stable. I didn't check, I have to say. In the worst case, you can pre-populate the virtual address space, but
Just to make sure, am I right to assume that if you want to flash from like this log to, for example, SSD, then the speed would be kind of like limited by the speed of writes on SSD, since
yeah,
it's
sure.
probably less than non-volatile memory, or it would create a bottleneck in this. Like not
It
bottleneck,
creates a
but
bottleneck. It's exactly what we observed here in this curve. At the beginning, we are very good because we run at the speed of persistent memory, and at some point we saturate the SSD, and we run at the speed of SSD. So it's very useful when you have small writes for when the number of writes is not huge. In this case, you win because you have the time to propagate. But of course, if you have an intensive write application, at the end, the bottleneck will be the SSD.
Again, you tested on databases not because you tested like you copy a movie that has 10 gigabytes of files that you need to move. It's, as I understand again, it's a solution for some kind of live data.
Exactly.
It's not a big size of
Yeah.
data. You need to push it back to some persistent storage. And that will speed up databases very interesting way. Because right now, all databases are based on some operational system limits. And what we see here, that's the kind of booster that could help us to go far from what we have from the default kernel in Linux, an example. So if we are looking in the oracles, that could help us in some cases, because we could build it in a different way how to use drivers.
Yeah, sure. We made some tests with FTP. And of course, if we copy very large files, we bottleneck the SSD immediately, and it's totally useless. No, it makes sense when for databases where you don't have so many writes, it's interesting. Okay. We can close the session, as Pierre said.